In this lesson, we shall focus on linear algebra, the module MAM2000W 2LA, and we shall solve past examination questions. In this particular lesson, we shall focus on first the 2021 June examination for the module 2LA, and we start by solving the fourth question. Right, now section B has question 4 in it, and it was actually out of 14 points. We let S be the set that contains matrices A, which are elements of the vector space of 2 by 2 matrices with entries in R, such that the determinant of A minus A transpose equals 0, and the matrix B, or rather the set B, of 2 by 2 matrices is given. And obviously, this is very interesting. Now, I'm just looking at this question, but the set B is having how many matrices in it? Okay, so
3.
it has 3, but now 2 by 2, you see, immediately when you say M2 by 2, right, when you say M2 by 2, it means a vector space of dimension 4.
Oh, yeah.
Okay, so the dimension is always this product of these numbers. Okay, so dimension equals 4. In other words, saying that if you're dealing with the dimension of the vector space, as much as we write M, but it is a vector space of all 2 by 2 matrices, which has dimension 4. If this thing is 2 by 3, then the dimension is 2 times 3, which is 6, and so on and so forth. But now I'm saying that because the examiner is likely to ask a couple of questions here, like, can this be a basis of M22? I mean, that is an immediate question, because M22 has many bases. Okay, they have many bases, but the truth is all the bases of the same dimension. Okay, all the bases of M22 are isomorphic. Okay, so now obviously there's the theorem there that needs to be proven. Okay, so but let's start with this one and answer this particular question. Now, S is closed under scalar multiplication. Prove what is prove the following. Right, S is closed under scalar multiplication. Is it true or false? We're looking at this one. So we try and check this. But obviously, because we're dealing with S, and now S itself is a component, is part of a vector space of certain matrices that satisfy this property here. So yeah, it is expected that this has to be the case. So now, it is certainly a true story, but let us prove that. To prove that, we actually take a vector and a scalar. All right, so to prove a scalar multiplication, we take a vector. So now a vector would be this one matrix here. So we say let A be an element of S, and we take lambda, a scalar, to be a real number. Okay, so yeah, this is what we have. If this is the case, then we have the following. So we take always, this is how we start the scalar multiplication proof, because normally they will ask if this is about subspaces. We call this section subspaces. So now, if need be, we're going to have a chance to go through the study guide and discuss the study guide's approach into every section. Okay, now that will be very important. Okay, we're gonna look at and just look at the study guide's definitions, the study guide's every section. That will also help us to understand this topic, this particular module more. Then what then do we say? Because A is an element of S, it must satisfy the property of the matrices. What is the property? It is that the determinant of A minus A transpose equals 0. Right, so this is exactly the case. Now, all the elements of A, if you take an element of A, it must satisfy the condition of the element of the matrices in A, and the condition is that the determinant of A minus A transpose must be what? Must be equal to 0. And if that is the case, we then say, hence we have the following. What do we then have? We have the determinant, right? So we have the determinant of, we multiply the, so we multiply this particular matrix by a scalar, right? If we actually do that, so there are 2 ways to do it. There are certainly 2 ways to do that. So we can start as follows, or we can start differently. So in other words, one way to do that is to multiply each of these matrices. But yeah, I want to do things uniformly. You can start by saying lambda A minus lambda A transpose. Okay, it's the same thing. So you start by saying you are actually multiplying each of the matrices by the scalar, and you want to show that this property holds true. And if you look at that very carefully, you can even write this way. I think it's nicer and much smarter to write this way, and then say it is, you put the transpose here. So you take lambda A minus lambda A all to the transpose. Okay, and if you take very carefully, what this means is, okay, the lambda is a scalar, so it doesn't affect anything. Even if you take the transpose of a number, it remains a number minus A transpose. And now the transpose is going to be on the matrix, the transpose symbol, meaning therefore you have the determinant of this minus A transpose. Right, so now when we have this, what then do we get out of this? These are 2 by 2 matrices. These are 2 by 2 matrices. So now, if you need to find the determinant of this particular lambda, what is it exactly the same as? So we realize that it was such that this lambda multiplied each of these 2 by 2 matrices, and therefore, if you take it out, it becomes lambda to the order, right, to actually the number of rows of this particular matrix. So this is a 2 by 2 matrix, and therefore it becomes to the power 2. Right, the determinant of, okay, you know, this is the property of the determinants. I've seen that in your material. They've started this module with the determinants. So, you know, sometimes a student can take a lot of time trying to read the determinants alone, but yeah, but they remain very, very basic. But one property of the determinants is you look at the size of the determinants. Yeah, determinants are only defined for what? For square matrices, right? So then you need to find the determinant of a scalar times the matrix. If you take out the scalar, it becomes square because the matrix is 2 by 2. If it's 3 by 3, it becomes like cubed. Okay, so yeah, it's property of the, it's a property of the of determinants. Right, yes. And the determinant of A minus A transpose is 0 for the matrices. Yes, so that now the determinant of A minus A transpose is 0, and therefore this result is 0. And therefore, what therefore does this mean? So it follows that, right? It follows that. So it follows therefore that lambda A is an element of S. Okay, very, very nicely written proof, because we just realized that, okay, because we actually therefore started with, so we can even include a small line here. So this becomes our script of reasoning to then say, if we let a vector, so always when we prove scalar multiplication, there are two things we need to take into account. We take a vector and also a scalar. And then we can write and say, we need, okay, you can always write this. We need to prove that, because sometimes it's very important to have an objective in mind when you need to write a proof. So you need to prove that lambda A is an element of S. So now when you take one vector element from the set and also take the scalar from the field, now what you need to actually realize is you need to prove that scalar multiplication holds. So in other words, when you multiply the vector by the scalar, the result is in S. That is what you need to prove. That is what you need to show. So, and we showed that that is the case. And the strategy here was to then say, we start with that matrix. So now to have the lambda A in S, So we started by saying, okay, in this determinant definition, wherever there is A, we put lambda A. Wherever there is A, we put lambda A. And then we raised it to transpose, and therefore we showed that this result is 0 because the lambda A matrix satisfies and gives us 0. It means, therefore, the lambda A becomes a member of the set S, and therefore we are thrilled and we're done with this. We're done with this. Next point. Right, so scalar multiplication. So in other words, it means lambda A is an element of S, and this means that S is closed under scalar multiplication. It is enough to prove that. Next point. Right, we look at the next point. So the next point is point B. We need to prove or disprove each of the following statements. Now, we need to show that S, okay, prove or disprove. S is a subspace. Okay, so this is a very, very interesting because we have already proven that it is what? It is
It's
closed
closed
under scalar multiplication. It is one of the requirements. But now, what? Yes, definitely. So now, what other thing do we need to show? So now it is getting closer to being true because one thing that we need to show is therefore that it is not empty.
closed. Oh yes.
Yes,
And
we need to show
it's
now.
not
Now we need to show that it contains at least a zero vector. At least the zero matrix is here. But surely the zero matrix is here. No doubt. No doubt. So in other words, you then say true. To show that, okay, we say that true. S is what? S is non-empty. Okay, so we then say S is non-empty and closed. Okay, we'll explain this. And closed under
scalar multiplication.
yeah, under scalar multiplication. Well done, because we have proven that. So it's closed under scalar multiplication, right? It is closed under scalar multiplication and what? And also, now what else would that be in the case?
It should be closed under addition.
It should be closed under addition. Can we show that? So now that is, yeah, that is what. So yeah, it is closed under scalar multiplication because we've proven that, but it's closed under scalar multiplication and addition, and need to justify the addition part.
Yeah.
Okay, but it is closed under vector addition. Okay, so the kind of addition is the addition of vectors because yeah, what we deal with two kinds of objects, vectors and scalars. Okay, so yeah, it is closed under addition, but also it is closed under scalar multiplication. Why would this be the case? And obviously we would be in a position to have that proven. There's obviously no doubt there. Okay, but now what is very important is to say it is not empty and it is closed under scalar multiplication. Okay, scalar multiplication can be seen to imply addition. How? So once a set is closed under scalar multiplication, because now if you are to look at the determinant, we look at the determinant of what? Of lambda A minus lambda A transpose. And then we showed that this was also 0. And therefore, it showed closure under addition, under scalar multiplication, excuse. Now, because now under addition would mean, what would addition mean? Right, so addition would mean therefore that you are adding this. So now you can look at 2A minus 2A transpose. 2A minus 2A transpose. And then now that would mean you can look at this as what is A?
What? Oh.
A. So now, yeah. So now you can be in a position to do what? To make a deduction about what is happening, because now it's under scalar multiplication. This scalar can be a number that produces some multiples of the matrices. All right, so in any event, it produces a matrices that has implications about addition of vectors, you know? So that now, because it is non-empty and is closed under scalar multiplication, and addition can actually be observed in this sense. So in the end, then, without having to waste a lot of time here, because they do not expect lots of details, but now it's ready to say it's true, S is non-empty. But now there are more details. Okay, why would you say it's non-empty? Because it contains a zero matrix. Why?
Yeah.
How do we know? How do we know? Because the zero matrix has determinant is 0 here that we're dealing with. So the zero matrix automatically has zero matrix because has zero determinant. How? Because the determinant. Okay, so now because the determinant of 0, 0, 0, 0. Okay, we're looking at the matrix A. That is what? That is 2 by 2, 0. We're looking, yeah, we're just dealing with A, that is 0, and then we have 0, 0. Okay, I mean, we obviously we're writing like this, but we can write logically, and writing it logically. So we have the determinant. Okay. So now we have the transpose here. Okay, so we'll look at the case when A is only what? Is the zero matrix, and so that we can say it's not empty because it's not empty since, you can even say that, it's not empty since the zero matrix is an element of S and it has zero determinant. Okay, then now here you come. The transpose of the 0 is 0. And then the 0, 2 by 2 minus the 0, 2 by 2 matrix, it's still 0. Zero matrix minus itself, it's 0. And therefore the determinant of this is what? Is 0. So that now we're getting 0. So that indeed it is true, therefore, that S is not empty since the zero vector is there. Okay, because not empty means at least there's only one element that must be there. It is the 0 vector. You know, because what is the smallest vector space? Okay, I'm just mentioning that. Out of all vector spaces, what is the smallest vector space?
I think the one that contains the 0 vector.
Yes, well done. It's only this one, the one that's containing the 0 vector. That is the smallest one. You get the point? Yeah, this vector space contains only the 0 vector. So the smallest one is, so now that is why always if we need to show that it's a subspace, something that you need to first know is that it must contain at least a 0 vector. Then it becomes a subspace, because if there's no 0 vector, then it cannot be a subspace, it cannot be a vector space. So we need only one element, and then there can be other elements as well. Okay, we move to the next question. Right, so we see.
Did you finish proving under addition?
Okay, that's a good point. Did we finish proving under addition? That's a good question. Did we actually finish proving under addition? Well, we actually obviously commented on the fact that S is closed. Okay, let's elaborate on addition. Let's elaborate on addition. Right, because I can see that sometimes I don't really expect much detail, but now for the sake of marks, it's very important that you attach the details here. Okay, I would imagine that if you say mathematics, if you say it's not empty, there has to be a reason for that. To say it is not empty because it contains, what element does it contain to say it's not empty, you know? So as I said, it contains the 0 vector. The next thing is to say it's closed under scalar multiplication because we proved that. And then now scalar multiplication has implications about the addition part, the vector addition part. But now you can always come to the vector addition part. So proving vector addition, in general, you would have to prove that. But I can see that sometimes like they don't provide a lot of space because it's like,
because they give us papers for working.
Yeah, that's the thing. So they give you papers, yeah, definitely. So proving vector what? Vector addition. Right.
Oh, it's the same with scalar multiplication.
Yeah, it's the same
thing.
Yeah,
we can move. It's fine.
Yeah,
we
that's
can
the
move
thing.
to the next question.
Because with lambda A, you can look at multiples of that. As lambda A, if lambda is 2, then it's 2A. And then it's A plus A minus A plus A, which therefore we've proven already. So once you prove scalar multiplication, you can make inferences about the fact that addition surely follows. Addition follows. All right, so but I mean it's still possible. It's possible to give it its own line of proof. But once again, I can see that maybe they give you papers for working, but the answer books do not have a lot of They appear not to have
Space.
a lot of space for writing too much. And sometimes I believe the space is indicative of them. But sometimes the spaces are not fair. Sometimes the spaces are not fair because the spaces are too small. And now, I don't understand how you guys are doing it. Okay, but obviously they're trying to cut out on paper because how much space should they provide? And I think that obviously in the end, they can't provide you with a book of papers when maybe the students can cut down and we can save paper and we can save paper, we save trees as well. Anyhow, right, prove or disprove each of the following. Right, so now we are then saying this matrix is an element of the span of B. Okay, these questions always repeat, and I remember this question we did it last time in one of the previous examinations, you know. And now when we did this question, there was like we need to take note of the following. So to prove or disprove the following, the truth is the first thing is we need to let. We need to let because how many elements are here? Okay, there are 3, so we need 3 scalars. All right, so we need to let lambda 1, lambda 2, and you can call them like A, B, C. So we need to let lambda 1, lambda 2, lambda 3 be members of the real number. Okay, and if this is true, we take these to be real numbers. Why? Because this thing here, it's a vector space with real entries, and the understanding is that the field from which you take the scalars is real, is the set of real numbers. Then now we can be able to take the lambda 1 and multiply the first matrix. Lambda 2 multiply the next matrix. Lambda 3 multiply the next matrix like this. And if we do this, the result of this is what? Is this one here. Is this one here. And this is exactly minus 1, 1, 1, 0. Okay, so we are then effectively saying we can take scalars as scalar and multiply this one here, and we can take a scalar multiply this one here, and then take a scalar multiply this one here. And then if multiply these ones with scalars, and therefore it is exactly equal to this. But also we need to open our eyes and open our eyes. What do we open our eyes to see? We open our eyes to first check if the examiner is not playing a trick on us. If this member is not already there, or at least this member, if you multiply it by a number like negative, so that this is 1, negative, negative 0, negative 1, negative 1, 0, is it? Yeah, so you don't have the negative 1, negative 1 here. Okay, 0. So in this case, therefore, obviously, in the end, if this matrix is an element of the span, it means, therefore, this matrix can be written as a linear combination of the elements of the set B. Okay, so which is what we've done. They always ask the question of the span. So then what do we do next after this? Then we need to check if this relation holds true, but we need to continue. Right, we need to continue to check if this makes sense. Right, we need to check if this does what? This makes sense, but also if this relation is such that it has unique solutions or not. Okay, right, so, and now we actually obviously see if there's a solution to this or not. Okay, so if there's a solution to this, it means that yes, it can be written as a linear combination. Sometimes there's no solution to this, it means in which case, therefore, this one is odd. It's an odd matrix out of the picture. First things first, so let us perform some multiplication together. Right, so we're going to multiply lambda 1 minus lambda 2, 0 equals minus 1. Top. Lambda 1 minus lambda 2. Okay, you can just multiply. Lambda 1 minus lambda 2, 0. For the top entries, you can write like this. And then the next one, this one, is lambda 1, 0 minus lambda 3. Right, so with lambda 1 minus lambda 3. And then we come to this one, which is actually minus lambda 1 plus lambda 3. And then now we come to this one, which is exactly 0, lambda 2 plus lambda 3. Plus lambda 3. and we have this. Okay, this is exactly what we get. But from this, we have interesting stuff to do, because now we have exactly what? Lambda 1 minus lambda 2 equals minus 1. Lambda 1 minus lambda 2. And then now here it equals minus 1. Okay, we're going to just break this into a couple of matrices. Minus lambda 1 plus lambda 3 equals 1. Minus lambda 1 plus lambda 3 equals 1. Okay, so, right, lambda 1 minus lambda 3 equals 1.
1.
Yeah, lambda 1 minus lambda 3 equals 1. Lambda 2 plus lambda 3 is 0.
Yeah.
Right, lambda 2 plus lambda 3 equals what? 0. Okay,
Yes.
what is the meaning of this? Now, we do component-wise comparison, so which means that we have lambda 1 minus lambda 2, and the result is minus 1 to compare this one with this one corresponding entries. Next, in any order, we can take now this one. Right, so we have minus lambda 1, and then we have plus lambda 3 equals 1. Next, we have lambda 1 minus lambda 3 equals 1. Last but not least, we have lambda 2 plus lambda 3 equals 0. So this produces a matrix like this. Now, this matrix here, we can be able to, we need to solve for the values of lambda here. And this matrix is very strange. Why is this matrix a little bit strange? How many, right, yeah, okay. This matrix is a little bit strange. Okay, but now I'm going to explain why it's strange. Right, let's write this. So it's going to be 1 minus 1, 0 minus 1, augmented. Okay, sometimes in your school, they don't put a line here. Okay, right, so you can have here next, you have minus 1, 0, 1, 1. Sometimes if you augment, you put a line.
Yeah, so
okay,
we can.
so that they don't get mixed up. Okay, right. And then here you have 1, 0, minus 1, 1. Okay, and then you have 0, 1, 1, and then 0. Okay, you have this kind of a matrix, and this kind of a matrix is exactly the same as the one your teacher got in your school. Okay, now if you look at this one, what do we do with this? What do we do with this? We solve.
Right.
Right,
Yeah.
we solve this. Let me make this bracket bigger. Okay, we solve this one. Okay, to solve this one now, but once again, you see, now this matrix, if you have 3 unknowns, you must have 3 equations. But now you have 3 unknowns, lambda 1, lambda 2, lambda 3 are the 3 unknowns, but the equations are many. 1, 2, 3, 4. Problematic system, this one. Okay, let us actually check what we're getting here. So here we already have a 1. 1 minus 1, 0. Minus 1. Row 2 plus row 1. 0. Minus 1, 1, 0. And then row 3 minus row what? Row 1. 0. 1. Minus 1. 2. 0, 1, 1, 0. Like so. Okay. Okay, you're getting to this point. And then now we need a 1 here. And then we need zeros above and below, because this is our next pivot. Right, so now we then multiply row 2. So this one is going to be minus row 2. Okay, we normally write minus 1 row 2. Minus 1 row 2 like that. So, right, neatly speaking, I know that your school has a different way of writing these things. Okay, minus 1 times 2, so that it's 0, 1, minus 1, 0. And then now we're going to get, we need a 0 here. So we can say row 1 minus row 2. Right, getting a 1, 0, minus 1, and then minus 1. And then here we have row 3 plus row 2, which is 0, 0, 0. Aha, here comes a big problem now. Okay, we're adding row 3, but you're also adding to row 2, so that you add this, you add this, you add that, and then you get a 2 here. And then this one is 0, 1, 1. Okay, yeah, we can get something here. We can get row 4 plus row 2. Right. row 4 plus row 2, because we want to get some more zeros here. There's a chance to just get a zero. Just get a zero here using row 2. So now if you then say row 4 plus row 2, then you add this here, you get a 0, and then you add this, and you add 1 and 1, you get a 2 here, and then you add a 0 and a 0, and you get a 0 here. All right, now this one is the problematic one. It says the 0 equals a non-zero number. It says 0 equals 2, and this is false. Now, Mr. The examiner, obviously this is the most problematic of all these, and therefore we are able to then say it actually gets to this point. And from this, we're able to see that here there is just no. Okay, let's write next point. So, okay, so we're able to see that this one has no solution. So now it means you have 1, 0, minus 1, minus 1. 1, 0, minus 1, minus 1, close. Right, and then we have 0, 1, minus 1, 0. Okay, 0, 1, minus 1, 0. 0, 1, minus 1, 0. And then 0, 0, 2. Okay, good. 0, 0, 2. Hey. Okay. Yeah. And then 0, 0, 2, 0. 0, 0, 2, 0. All right, we interchange. So now we have row 4. We interchange row 4. Okay, because the practice is to put the 0 row at the bottom. So as a strategy, just put the zeros at the bottom. So 0, 0, 0, 2. 0, 0, 2, 0, and then 0, 1, minus 1, 0, and then 1, 0, minus 1, minus 1, like this. Okay, so now we have this, but now the bottom row is so it reduces to this, and this is exactly what your teacher got. So what is the meaning of this? So this shows that, what does it show? It shows that the system is inconsistent. Okay, I was going through your study guide. I was going through the study guide because I wanted us to include more things from the study guide, but I realized that the use of the word inconsistent is actually obviously the usual meaning to say that there is no solution. Okay, so the system is inconsistent. Hence, because it is inconsistent, it means this claim is false. Right. What is the claim? It means that the minus 1, 1, like that, is not an element of the span. Of the span of B. You see, they claim it is an element of the span, but it is not an element of the span of B. Right. So this is the standard way of reasoning. And with this, we're able to say that because the question was prove or disprove. So what have we done? We disproved.
Disproved.
Yeah, we disproved because in mathematics, a false claim is not proven, but it's disproved. And now it's disproved. How so? A tricky question would have been prove or disprove that a given element is an element of the span. So, I mean, a trick question would have been guess a 2x2 matrix that is not in the span of this. Find a 2x2 matrix that is not in the span of B. So you'd have to like guess some numbers. And then, but that would take very long. And at least the examiner gave you and then said, obviously, try that. Right.
So how do you find, how do you approach that question?
Yes. Sorry? Yes. So because another question would have been find a 2x2 matrix that is not in the span, because we have seen that this one is not in the span. Because if they can say find a 2x2 matrix that is in the span, this one is in the span. All these ones are in the span because they're already in B, so they're in the span. All right. So those that are in B that are in the span. But the examiner can say, find a 2 by 2 matrix that is not in the span. That is not in the span, because if they say find a 2 by 2 matrix in the span, you can just pick the first, the second, or the third one. Okay. So you're right. But find a 2 by 2 matrix that is not in the span. Okay. If the examiner would have said not in the span, find it. That would have been very tricky, because any student can get their own matrix, you know, and students would deviate from some students would deviate, because these matrices have zeros, ones, and negative ones. You know, a student can come up with matrices that have 2, 3, 4 numbers like that. Okay, which obviously can possibly work. Okay, how do we approach that? This is how you would approach that. Because of this question can alternatively, okay, the examiner was thinking about this. Alternatively, first we say this. We can see that any matrix in the span, right? Any matrix in the span of B, must be on the form. Must be of the form. Right, we can see that. Right, alternatively, we can see that any matrix in the span must be of the form A, B, minus B, C. Okay, take a look at these and be able to, yeah. Okay, because you can see that any matrix in the span is such that this number is different from this number.
Okay.
Because here there's 1 minus 1, here there is minus 1, 0, and then here there is 0, 1. In which case, therefore, in general, one claim would be, okay, a student can say if there is a number here, then the second one is it's negative. Okay? But it will be false when it comes to this matrix, because this one has a number whose negative. If you multiply this by negative 1, you don't get 0, you get a 1. So it's not true that. So now what you're able to see consistently is therefore that this number and that number are sort of different, because here it's minus 1, 1, and then minus 1, 0, 0, 1. So they're different, these numbers. So that's why you can call them AB. But if you look at what happens in the diagonal like this, if ever there is a 1 here, there's a negative there. Okay, this one you can't say 0, 0, because you can see that if this is 0, this is negative 0. Or this negative 0, but negative 0 is still 0. But here it's very clear. There's a negative 1 who's negative. If you multiply negative 1 by negative, you get a 1. So which means therefore now we have a minus B and a B. Right. So that in the end there, what then you're having is, if ever you have a number here, we have a negative number here, it's positive, it's there, or vice versa. So in other words, you have a negative, a number here whose negative is there. There's 1 here, negative 1 is here. Right. If ever you have a negative 1 here, you multiply by negative, and then it becomes a plus 1. All right, and then there is a C here which is also different. So this will be another way to make this very clear, that we can see that any matrix in the span of P must be of the form that. And therefore, we can see that since these are not negatives of each other, because it's just 1, 1. So this one, and hence this minus 1, 1, 0, is not in the span of B. Why? It's not in the span of B because it's not having the kinds of negatives here. Okay, it's just an observation, but this is tricky. It might take time in the exam to look at the number patterns, because it's like number patterns, and patterns take time. What is the quickest way to do this in the exam? The quickest way to do this in the exam is to say, prove that something is in the span. You write a linear combination that is equal to that element we're interested in proving is in the span.
Okay.
Okay, good. Now, that is what obviously we do. Let's look at the next point.
Oh, sorry. I also wanted to ask,
yes,
if let's say we get that the matrix has infinitely many solutions, then does it mean it's part of the span?
Okay, that's a good question. If it has infinitely many solutions, does it mean it is part of the span? Yes, it has to be part of the span. It has to be part of the span. Why? Because it means that it can be written as a linear combination of those elements. You know, it can be written as a combination. We check if that is true or not. Right. So the span is not like a basis. So the span is not like a basis because a basis would require that the coefficients, all of them, be zero. You know, I mean, if we're dealing with the basis, you would require that if you write this linear combination, the lambda 1, lambda 2, lambda 3 be all zero.
Yes.
Okay, that would be true for the basis, but for the span, they need to just be numbers. So as long as, but now if you have infinitely many solutions, it means there are some numbers that are going to work. So yes, the presentation therefore becomes true. Okay, so we move to the next point. Right, so now we need to prove or disprove each of the following statements. B is linearly independent. B is linearly independent. Right, so let us prove this part. Now, to prove linear independence, okay, yeah, obviously, these, as I said that in the beginning, one thing that is very strange, always strange, because we're dealing with a vector space of 2 by 2 matrices of dimension 4. Right, of dimension 4. Right, so if the dimension is 4, in other words, we're saying the dimension of M2 by 2. Right, the dimension of M2 by 2 is 4. Okay, vector space of all 2 by 2 matrices is 4. Okay, what makes it strange? Normally, this one now has fewer elements. So obviously, it's subspaces, because it has fewer elements and therefore it cannot span M22, for example. Okay, that question can come at some point.
Cannot span S.
Yeah, it cannot span S. Okay, yeah, right. So that's just what. So now, right. So you have that. So it cannot, in particular, span M22. Okay, I'm mentioning that M22 because M22 has dimension 4. We're sure about it. Okay, right. So now, prove or disprove each of the following. B is linearly independent. Okay, now let us check these. But obviously, now this one can be seen also from the previous calculation, you know, but you already have something from the previous calculation, so we don't need to sweat. What did you get from the previous calculation? We need to take it from this matrix here, because we must write a linear combination. Yeah, let's write the solution as it should be written, and then we shall actually make use of that. So how do you prove that B is linearly independent or linearly dependent? Okay, we need to first take the scalars. We can call them lambda 1, which we have already done in the previous question, lambda 3, and therefore we're going to refer to the answer there. But to prove linear independence, you need to take 3 scalars because there are 3 vectors and let them be an element of R. Let this be the case such that. Let this be the case such that. So we have this. Such that we have lambda 1, lambda 2, and then, okay, linear independence, we write this one and make it what? And make it 0. And make it the 0 matrix. But now, we already have reduced everything. What did we do? We got to that matrix that was this one. Okay, because now it's the same thing that we're doing, like we did in C. So in the exam, obviously, you guys are working under like time constraints, and therefore it's very important that you are able to make observations about, you know, the kinds of things that have already been done, and then you don't waste time by repeating processes, and then you can then quickly copy answers you have. Right. So now you then say yes. So I mean,
why are we?
Yes. Please come again.
Oh, with linear independence, we make the matrices equals to 0.
Yes, we make the linear combination. Yeah, we make the linear combination equal to 0. Why? Because We always do that so that we can see if the lambda 1, lambda 2, lambda 3 are all 0 or not.
Or 0, okay.
Yes, because if they're all 0, then it's what we want. Then we have linear independence. Okay. But now, because they might not be 0, so we force everything to become 0 and see if it works. But in this case, we already have something. What do we have here? Okay, let us write a little bit of the steps here. Okay, we wrote this matrix. Yeah, we can come to that. We wrote this matrix and then we row reduced everything to 1, 0, minus 1, minus 1. Okay, I'm just copying that matrix because we go to it. And then we have 1, 0, 1, minus 1, 0. And then we got this one, 0, 0, 2, 0. And then 0, 0, 0, 2. Okay, so we got to this matrix here. But remember that we got to this matrix because we had taken that matrix that they gave us there for the span. Okay, so we took that matrix that everything was equal to this, minus that, minus that, minus that. So we made that linear combination equal to this. Okay, so obviously it's not in theory, it is actually in practice because we made that linear combination to be equal to this. Right, we made it to be actually equal to this matrix here. But now we're making it equal to 0. Meaning this right-hand side is going to have zeros only. Okay, so now we're going to check if this is going to work. So it means that this matrix now is going to be like this. Okay, so in other words, using C, using C, we can write the matrix like this because now it's going to be everything is 0 here. Now we check, is this true? You see, the problem was the 2 which was here, but now we can see very well that everything is 0 now. So now then the question then becomes, because everything is 0, what then is the story? Is there a solution or not? Okay, yes, but not only a solution, because we're able to see clearly that we have 0 here, and then we can multiply this one by 1/2 and then get zeros here because of a pivot here. Now, because of the pivot that is here, we are able to make the following conclusion, that there is a solution here, but this solution is unique. Hang on, can we do this? All right, so we can just play around a little bit. So we're gonna have like, okay, sometimes I was taught by this other lecturer. This other lecturer always said, if you find a 0 row, just leave it.
Yeah.
Okay, yeah, okay, just leave it and throw it out so that now you're dealing with fewer rows because why carrying zeros, okay? But other lecturers came to me and said, you write all this, all the rows there. So, okay, now I choose what gospel to take, you know?
Yeah.
So, but now in the end, then multiply by 1/2 of row 3. Okay, 1/2 of row 3 then is going to produce a 1 here. And then with row 1 plus row 3, 1, 0, 0, 0. Row 2 plus row 3, 0, 1, 0, 0, 0, 0, 1, 0. Okay, this is what you're going to have, 0, 0, 0, 0. Right, okay? So that in the end, you're getting to this. And this means that lambda 1 is lambda 2 is lambda 3 equals what? Equals 0. Okay, because of this, okay, we need to write to this point in the exam. We need to then say, therefore, B is linearly independent. This is linearly independent. Okay, we're able to see, therefore, that B is linearly what? It's linearly independent. It's linearly independent, and these scalars are 0. Okay, it's linearly independent. Okay, why do we say it's linearly independent? Well, the truth is, it is linearly independent since this is the case. Okay, the linear independence follows from the fact that this relation is called a trivial. It's called trivial. It's a trivial linear relation. Why is it a trivial? What is a trivial linear relation? A linear relation is trivial. Well, it's linear because of the fact that we're doing linear algebra. Okay, but now trivial means that the solutions are all zero. Okay, then the lambda, the scalars are all zero. Then the relation is what? It's trivial, right? So we're done. We continue to the next point, and that is exactly the answer. So now, right. So yeah, we can also write it like this. The answer. We can always write it like this. We can always write it like this and say it is true. It is true that it's linearly independent if the right-hand side or the right-hand side of the equation right-hand side of the equation in the answer to C is replaced by the zero matrix. By the zero matrix, we replaced the right-hand side of the equation in the answer to C is replaced by the zero matrix. We put zeros on the right. The reduced, right? The reduced matrix, right? So the reduced matrix of the resulting homogeneous system shows, right, of the homogeneous system shows that the system has a unique solution. Has a unique what? Solution. Has a unique solution. Lambda 1 equals lambda 2 equals lambda 3 equals 0. So this is the kind of stuff that we, showed that the lambda 1, lambda 2 equals lambda 3 equals 0. And therefore it is true that B is linearly what? Linearly independent. All right. So we continue. Right. We continue. We continue. Right, so now let's look at the next question. Okay, prove or disprove. I was waiting for this question.
Okay.
I was waiting for this question. I was waiting for this question because I said automatically the fact that this one is of dimension 4. Okay, yeah, because the examiner did this on purpose. So the fact that dimension of the 2 by 2 is 4, yet there are 3 elements here, would mean that B is not a basis for M22.
Yeah.
Okay, but now the examiner is saying prove or disprove, but it is based on the dimensions. Based on dimensions, it's already not, And now I want us to therefore, obviously, spend some time to analyze this with so much caution. So, and the immediate answer is that it is false. It is false. Why? Because M22, the vector space of all 2 by 2 matrices with real entries, has what? Has dimension 4. Right, good. Has dimension 4. And hence, every basis every basis for it, every basis for it has 4 elements. Every basis for it has 4 elements, while B has only how many? How many elements does B have? There's only 3. It's only 3 because of that. In fact, particular, I was just waiting for that. So, and obviously, I mean, if B were to have 4 elements, it could be a possibility, you know, you could start working it out. But at this point, how would you prove mathematically that it is not the case? Because we use the notion of dimensions here. We use the notion of dimensions, and I think that it is what is best to use, you know? It is what is best to use for this particular question. We move on to the next point.
Okay, so how are we gonna prove if we had 4 elements in the
We're to prove that the set with 4 elements is linearly what? We're to prove that the set with 4 elements is linearly independent.
Yeah.
Okay.
Oh, so if it's
if the set with 4 elements is linearly what?
Independent.
Then it would mean that it's a basis, you know?
Also,
yeah,
okay.
but because you see, there are 2 things to prove for a basis. What are the 2 things to prove that a given set is a basis? The 2 things that are there to prove it's that the set spans the vector space. That is the first. Because what is the job of a basis in mathematics? What does a basis do? What is a basis for? Why is a basis so important? Why is this kind of a set that we call a basis so important? Why? It is important because in mathematics, we're interested in dealing with sets that are generators of the vector spaces. Sometimes for us to deal with the vector space, we want to have a set that is going to generate the vector space, you know? So the set that is going to, how does a set generate a vector space? Because, can you give an example of a vector space? Okay, there's one we see in high school. This one. And then there is this one we see in university. Normally, okay, in our schooling curriculum, at least in South Africa, we do not have the 3-dimensional things, provided maybe you are doing AP math. I would imagine it might be there. All right. So now, but by and large, obviously for the 3-dimensional spaces, okay, so you have these. Now, this one is vector I, which is 1, 0. This one is vector J, which is 0, what? 0, 1. Now, there is this one here. And then there is this one here. And then there's this one here. So this one is vector I, that is 1, 0, 0. Vector J, which is 0, 1, 0. Vector K, which is 0, 0, 1. Okay. Many times in mathematics, we're interested in what is the basis for this vector space of this one. R3. This is R3. Okay, and this one is R2. Okay, these are important vector spaces. What do you call R2? We call it the Euclidean, Euclidean vector space. Okay, we call it the Euclidean two-dimensional vector space. Okay, vector space. Okay, we're interested in what with these bases? What these bases are, we want to be able to find a set that can produce all the elements here. You get the point? So the kind of set, okay, you see, the kind of set for R2 would be 1, 0, 0, 1. This is the one, it's the basis for R2. And then the basis for R3 is going to be what? It's going to be this one. You can start 1 0 0 0 1 0 and then 0 0 1. So this is sort of the basis for R3, and therefore it's of dimension 3 because it's able to generate the whole vector space. It means that if it's able to generate the whole, what is the power of this? Okay, I want to be able to actually discuss this. Now we are then saying it generates. How does it generate? Because you write like this. You write like this. If you write like this and you want to generate the whole R3. Because generate the whole R3, it means that every element, but no exception, like all of them, can be written as a linear combination of the basis elements. You know? Okay, so it means that with given numbers here, you can put some numbers. You can put some numbers here. And then if you put some numbers here, you can be able to generate all ordered triples. All ordered triples. Right, doesn't matter. So every vector, you can be able to generate it using this particular linear combination here. Okay, yeah, we can say more. It's just that it's more clearer, but yeah, but I'm sure that you sort of are able to get the drift. I'm sure that you are sort of able to get the drift. Right, so we continue. We continue. I want us, therefore, to look at more notions that are very, very important for us because every day we learn and the learning for us becomes the most important. Okay, now we're going to move to the next question. And when we move to the next question, our aim is to ensure that, okay, because you are learning mathematics and you want to make sure that, once again, we will make the effort to even go through the study guides, section by section breakdown, okay? That is very important. You see, the section, like the topic by topic breakdown, it's very important so that we are obviously in some good standing. With need be, as said already, we can try to get more time to do more, some double lesson something tomorrow, but tomorrow is the Monday. It will depend on you, as indicated already. You can, alert us and say, okay, you're gonna be free at this time, and then, okay, yeah, I'm just communicating with one student right now. Yeah, I'm just communicating. Yeah, I'm talking to you, but I'm also communicating to my other students. Right, so simultaneously. That's why I paused for a minute. I'm not moving. Okay. Yeah. Okay. I've not changed the slide because I'm communicating with my other students. They're expecting my communication. And okay, so now I don't want to leave them behind because I must tell them what is going on. They want to know what's up. They want to know what's up. Okay. They'll be like, okay, this guy is so quiet because normally in this slot, I put other students. Normally I put the school at 4 p.m. So I know that it started at 3, but at 4 p.m. normally I put the high school kids. There's some high school kids who are in matric. So normally I put them at 4 p.m. But now I know very well that the schools have just reopened and most of the kids are still warming up, They are still not yet in full swing. But I can see my clock has indicated that we are just some minutes after that. Okay. So this was some minutes after 4 p.m. We actually obviously need to do what? I need to communicate to them and remind them so that those students who might wish to join, I know that some of the students do not do exactly this kind of mathematics. They're expecting me to be doing school stuff now, but they will have a sense of the fact that because some of the kids sit at home and they're bored there. Okay, just in a minute, I'll revert and move to the next question. Some of the kids are sitting at home and they're bored now. They're like, okay, they think there's no class because the teacher did not say anything, Okay, because normally I communicate with the students on WhatsApp groups. I know that you're at university. I normally create some WhatsApp groups for the university students also. So right. And then now that is the case, and I want us to sort of right. So I'm just communicating with my other students in a split second, and then I'm gonna be right back. and then move to the next point, because I need to make sure that my students are not left in the dark. I cannot leave my other students in the dark. I know that I'm discussing something now, but my other students must also know what I'm doing. Must also know what I'm doing. Okay, I want us to therefore move to the next question. I've sent the messages to some of the students who are free at this time might just be like, hey, okay, let us see, let's participate in class and let's see what is going on. Let's see what is going on. Okay, right. So we're going to just move to the next point. Okay. Okay, let's see. Okay, yeah, we've already explained that one. This one, this thing, we've already explained that B can't be. Okay, there's a student called Ronewa. Okay, this student is joining, but hey, he's normally very noisy. Sometimes he's sitting with other kids because it's still school. And now he's sitting with other kids and it's trying to join. And when this kid is trying to join, then you hear the other kids talking in the background. And then we don't want that. But yeah, but I can see that it's still growing. Okay, but at least it's muted now. Okay. Okay, so remember that. Yeah. So right, so yeah, I know very well this kid joins. You see, I would hear the talking in the background. They join when they're talking, and we want to have one person talking, not everybody talking. Okay, right. So yeah, we good. So now I want us therefore to deal with this one of G. Prove it is prove each of the following. Now there's what we call basis extension. Right. So now this basis can be grown. We can add another element. We can add another element so that in the end, this one becomes a basis of that. Prove or disprove each of the following. If we add this element, will B therefore have 4 elements and the 4 elements doing the job? Hey, this element looks very familiar, this one. This element, is it the same as the one we saw that was not in the span? It looks like it's the one we saw that was not in the span. Let us check.
Yeah, it's the one. It's the one.
Okay, because now this element could not work. It didn't work. Because it did not work in the span, then it can't work. Okay, but now we need to just investigate that one. Okay, I'm just going back to see that element. Okay, you see, this element that was in the, we had to prove, but we realized that it was not in the span. -1, 1, 1, 0. You know? So we saw that this element could not be in the span, but the examiner is like, bring it again. And now he's trying to tease us. He's saying, hang on. Okay, but let us check. Let us check what's going to happen with this element, because it's -1, 1, 1, 0. Okay, it was not in the span, but now we realize that it was not in the span. Okay, now, but what then are we able to achieve here? Can we then say, if we actually add it to B, right, it might work. It might work. It might work. Now, a very interesting thing. Okay, it's not in the span, but it might work in the basis. So, but we need to check this. Okay, right. So, we need to check this. We need to check. How do you check this? Okay, you write a linear combination and see if it is trivial or not. Okay, so if in B, I mean, in principle, what you need to do, you need to let. Okay, because now how many elements? There are 3, and then you add this one. All right, so. Right, so we actually obviously now, right. Right, so we actually are looking at this very carefully. Right. Right. Okay, the way to do this is to take 4 scalars, generally, is to take 4 scalars and show that for it this to be a basis, then all the scalars are 0,
Okay.
That is the way to do it. And then now you don't need to sweat a lot. So you need to let lambda 1, lambda 2, lambda 3, lambda 4 be elements of R such that we have lambda 1 of 1 minus 1, 1, 0. And then, yeah, this is right here. Lambda 2 of the second one. And then lambda 3 of the third one. This one. And then lambda 4 of this one. Okay, you write like that. And then you need to prove that if it is a basis, then all these things must be 0, you know? But you write these to be the 0 vector, like that. If this thing is a 0 vector, then all these scalars must be 0. That's what you need to prove here. Right, so, okay, there are other ways, but now this is the most comprehensive way to prove. If this vector fails in this test, then it means that if you add it to this, if you adjoin this vector to that, to the set B, then it's not going to work. But okay, let us check. Hey, okay, it's a bit of pain to do this, right? Like the Americans say, right? So we have, yeah, okay. Somebody once said the Americans normally say that. Okay, and with the Americans, yeah, because they've done something strange in their country. I mean, a young boy, 20-year-old, just shot at the presidential candidate Donald Trump. You know, I mean, Donald Trump was there in Pennsylvania. He was having a campaign, like in South Africa when the Julius Malema, when the others were out there in the stadiums, were, you know, reading their manifestos. And Donald Trump was out there when one young man, a 20-year-old, climbed to the roof of a tall building and started shooting. And he was aiming at the head of the president. But because President Trump was, former President Trump, a potential presidential candidate, was busy talking. And when he was busy talking, he was moving. The guy missed the head because he was aiming at the head of the former president. He missed the head and he hit the ear. He hit the right ear of the former president. I mean, it made news in America. And now the security was so tight because they have the FBI's, they have general police, they have the secret intelligence security services. All those people, people said, we saw the boy climbing to the roof of the building. He had a rifle in his hand. And he was lying on the roof of a building, aiming at the head of the president who was speaking there. Because he was moving, the bullet went through the right ear. Now we saw Trump holding his ear, and I was like, why is he holding his ear? He screamed, holding his ear, saying, what's happening? Because he didn't know where the bullet was coming from. But this high school boy just shot at the former president just like that. But yeah, but I mean, the story we get from the US that in Pennsylvania, quickly they cornered the young boy. They took him down from the roof of the building. They shot him dead immediately. The FBI's, you know. But I'm saying that, I mean, the Americans themselves are popular. Some of them are said to be very notorious. The guns in America are a big problem. I think that is one thing. Because in America, somebody walked into a school a couple of years back and shot at school kids in a school. Just imagine. Killing so many of them. Can't remember how many school kids were killed. And normally killed by a young person who is just, I don't know. This young boy is 20-year-old killing many people. Why? You wonder. Okay, just mentioning that. All right, so you have lambda 1 minus lambda 2 here, minus now lambda 4. Okay, minus lambda 4, then it is equal to 0. Right, then we have lambda 1, lambda 2, lambda minus lambda 3. Okay, yeah. Which one should we take? Doesn't matter. We took this one, you can take this one.
Yeah.
Minus lambda 1, 0, doesn't really matter. Plus lambda 3. Okay, we must take them correctly. Lambda 1 minus lambda 2 minus lambda 4. If you take them wrongly, everything is a mass. Minus lambda 1 plus lambda 3, right, plus lambda 4. This is 0. And then now we have this one, lambda 1, lambda 2 is 0, minus lambda 3 plus lambda 4 is 0. And then now, let's check this one, it's 0, and then it's lambda 2. Okay, this matrix has been very popular today. Hey. But now, yeah, okay, but that's, we have added one vector. Okay, because we could use the C part. We could use the C part because C had three vectors, but now we're dealing with 4 of them. Okay, so lambda 2, and then, yeah, okay, let me see. For this one, 0 here, lambda 2, and then, 0. All right, so this is awesome, 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 awesome. Let's write a matrix out of this. Right, we have 1, minus 1, 0, minus 1, 0. Minus 1, 0, 1, 1, 0. 1, 0, minus 1, 1, 0. 0, 0, 0. Okay, this is the matrix we're getting. We need to just go on with the row reduction of this and see what you're getting. So like row 2 plus row 1.
Okay.
Okay, 0 minus 1, this one, 0 here. All right, row 2 plus row 1. So now if you add this one, it's going to be 0. You add this one, you're going to be minus 1. You add this one, you're going to get a 1, 0, 0.
Okay, so
Row 3, yeah. Minus 0. Okay, what do we want to do here? We want to just get all these. We want to know if these are all 0. And then this is going to be a pieces. Yeah?
Why do you have minus lambda 1 plus lambda 3? Is it not?
Okay,
Oh,
good.
sorry,
Okay,
it's my
minus this one, minus lambda 1 here, and then this one, lambda 3 by 1, and then
yeah.
lambda 4 by 1. Okay, well done, because now a small mistake here is going to make a huge mass. It's going to make a huge
Okay,
mass, and then you're going to like restart everything. Now, we are saying row 3 minus row 1, row 3 minus row 1, so it's going to be 1 minus 1, 0, this and that, 1, this and that, minus 1, this and that, 2, this and that, 0. And then we have 0, 1, 0, 0, 0. Okay, let's check. So now I'm going to put that matrix up here. Okay, we need to take all these matrix here. Okay, I don't want us to take a lot of time trying to move this matrix because now I want to put the matrix on our next slide so that I can discuss it. Right, so this matrix here becomes the following matrix. So it is 1.
Can you go back to the last slide?
Okay, yeah. Check what we have in here. Yeah.
For lambda 3, it's 0, 1, negative 1, 1, not 0.
Okay, let's check which one. Which one?
You see the matrices for lambda
Yes.
3?
Yes.
Yeah. It's 0, 1, negative 1,
Okay,
1.
okay, let's try. Are you saying the first row, the second row, the third row? Which one?
The third row.
The third row.
Yeah, it's
Okay.
1,
Yes.
0, 1. Oh, yeah, that's correct. No, the last row, sorry. Oh, I'm the one who's making mistakes.
All right, all right.
Yeah.
I'm happy that at least you'll be able to realize that because we're trying to avoid mistakes as much as possible.
No, I didn't make a mistake.
You-
There's lambda 3. There's lambda 3. Your
Lambda
matrix.
3.
Yeah.
Hang on, let me see now. Okay, let me see. Let me check if these matrices are correct. 1 minus
Okay.
1, 1, 0.
Mm.
Minus 1, 0, 0, 1.
Mm.
0, 1 minus
0,
1, 1.
1.
Well
Yes.
done, well done, well done, well done, well done. Okay, I'm happy that you're wide awake. Okay, this was going to cost us a lot of. So that we have lambda 3. Well done. So that now you have this one here, and then this is lambda 2, lambda 3, right? So, and that would be lambda 2, lambda 3, 0. So that's lambda 2, lambda 3, right?
Yeah, yeah.
Well done,
Yes.
well done. Okay, I'm happy that. So we're getting the same thing now.
Yeah.
All right, good, good, good. Thank you so much, because this is very important. And then now, at this point, it's only the last row that is affected. So it's going to be 0, 1, 1, 0, like that. Okay,
Yeah.
good. Now, I want us to take this matrix and put it here. So it's going to be, okay, please make sure that we don't make mistakes and every entry is written correctly. Right, so you have 0, minus 1, 1, 0, 0, and then we have 0, 1, minus 1, 2, 0. We have 0, 1, 1, 0, 0.
Mm.
Then now what do we do here? Okay, we're dealing with the pivots and other things.
Change.
Right, so we have minus 1 times row 2.
Okay.
0, 0. Then we have row 1 minus row 2. Okay, want to just reduce this one to reduce the Richard form, please. Right, so this is 1, 0, minus 1, minus 1, 0. And then this is row 3 plus row 2, which is 0, 0, 0, 2, 0. Row 4 plus row 2, 0, 0, 2, 0, 0. Okay? Now, this is awesome news, but we can see immediately that this is working. Okay? It is working because now, for example, we can, okay, interchange this one and multiply by half. All right, and then get zeros here. So in principle, okay, let's just show a bit more steps here. Otherwise, then, because we're learning and want to make sure that this is clear to everybody, let's not be lazy to just deal with the matrices. Right, because already it's working and you can see that. But, okay, multiply by 1/2 here, you get this. Multiply by 1/2 here, you get 0, 0, 0, 1, 0. And then 0, 1, minus 1, 0, 0. And then we have 1, 0, minus 1, minus 1, 0. Like this. Now, okay, what is the next thing we need to do here? Okay, I want us to squeeze the matrix here. So now when you get to this point, we can do what precisely here? Okay, we can put the matrix there, and then now let us have this matrix. And then this matrix now, we can even put it here. And then if we put this matrix here, we decide to interchange rows. What rows are we interchanging? We interchange the 2 bottom rows, right? Yeah. And then now, okay, we can see it's working, but already. Let's interchange the 4th and the what? And the 3rd. Okay, so which is 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, minus 1, 0, 0, 0, minus 1, minus 1, 0. So now, okay, we get to this point. Then now we're going to use this pivot to get this one. So it's going to be, for instance, row 2 plus row what? Row 2 plus row 3, row 1 plus row 3. Okay, row 2, row 1 plus row 3, 0, 0, 0, minus 1, 0. Row 2 plus row 3, 0, 1, 0. Okay, yeah. What have we done here? Okay, the zeros have put too many zeros in the first row. Okay, there has to be, how many entries are there? 2, 4, 4. Yeah, okay. I just put an extra one, 1 0 there. All right, so that it's 0 1. Adding the third one, it's 0 0 0. And then now here we have that is row 2 plus row 3. And then this is 0 0 1 0 0 and then 0 0 0 1 0. Right. So now we're getting this and then we're adding accordingly. Okay, let me just move this one a little bit. Need to squeeze this one. I could move on, but I need to just squeeze this one here. Right, squeezing that there, you're gonna just need row 1 plus row 4. 1 0 0 0 0 0 1. Okay, it's already working. 0 0 that 0 0 0 1 0. Okay, so in the end, what are we able to see here? We're able to see that lambda 1 is 0, lambda 2 is 0, lambda 3 is 0, lambda 4 is what? Is 0. Okay, what is the meaning of this? Because all these lambdas are 0, it means therefore we have a basis, isn't it? So in other words, and the conclusion is therefore to say, hence B union minus 1 1, this set here, minus 1 1 that is a basis. Powerful result this. Is a basis for M22R. It's powerful because this particular element was not even in the span, you know?
Yeah.
It was not in the span, yet now if you put in the basis, it is working. So, I mean, it is profound because we just checked it is working. And this is enough to then say, is this a basis? Yes, it is a basis. Hence, this is a basis for M22R. Okay, but obviously, there are other ways to sort of arrive at a conclusion to this one. And here is one story. We can explain these things here. Can explain. And one explanation, alternatively, we can go on to say, okay, it is true. It is true since any matrix in the span, of B must be, okay, this one is tricky to see, must be of the form, okay, it was the thing we made, the claim we made earlier. It must be of the form, so the element in the span must be of the form A, B, then minus B, that. We have that. Right, so we have that. Minus 1, 1, 0 is not in the span, okay? So you can use this description. It's not in the span. So, I mean, we can use these to say it's not in the span of B. Okay, so this is very powerful because it is not in the span of B, but also note that B is linearly independent. Linearly independent. Hence, right. So we know that B, we saw that B is independent, I think, somewhere. Right. Hence, okay, there is a theorem in the study guide. Right. So by theorem 2.1.19, it follows that B union that is also linearly independent. Also linearly what? Independent. Okay, so you see, this theorem is the one we're using. You say it is there in the study guide. Also note that B is linearly independent. So since B is linearly independent, moreover, this one is not in the span, is not in the linear combinations, in the set of all linear combinations, and therefore it follows that therefore it makes sense to say this is linearly independent by the theorem 2.1.19. So a student can use the theorem there and cut out the work to show that this is linearly independent because of the theorem. And right, hence B union that, to say if an element is not in the span, but also we have a linearly independent set. This linearly independent set can be extended to a basis. Okay, that is the theorem there. A linearly independent set can be extended to a basis. If this particular element,
only if it's linearly independent.
yeah, that's the thing. Or in particular, that is the theorem in 2.1.19 there. So it's all, so hence B union that is a set.
Okay.
Because B was at 3 elements, now we have 4 elements. Right, hence B is a set with 4 linearly independent vectors. Linearly independent vectors. Linearly independent vectors in M22R, which is of dimension 4. And the conclusion then is to then say hence B union -1, 1, 1, 0 is a basis. Yeah, it's a basis for M22R. M22R is a basis for M22R, like that. So obviously that is sort of the story that we have here. So it's something therefore that we can say. But what is the power of this description? Why is this standing, this description? It's standing on 2 facts. Okay, we wrote so many things, but it's standing on 2 facts. The first fact is that this vector we're adjoining by, we are adding, we're including. This vector we're including to B, we're adjoining to the set B. It's a vector that is not in the span, so it is totally disconnected from these in the linear sense, meaning it is not in the span, and therefore it is such that it's totally disconnected from this. But also that is seen from the observation we made that these elements here are such that if you have an element here, then if this one is an element, then its negative is there. If you have an element there, then its negative is there, something of that sort, so that we have B and minus B notion, so that indeed, obviously, this is not in the span. Because it is not in the span, we can therefore take a linearly independent set with fewer vectors and adjoin it to the fewer vectors so that we have the basis that has been extended. And obviously by theorem 2.1.19, a linearly independent set can be what? Can be extended to a basis. Okay, so yeah, this is the most important result. So we actually obviously have solved this one here. And we move forward. Let's check the next thing. We check the next thing. Okay, this one we've already done. Okay, this one we did in our previous meeting, question 5. So we're gonna move to question 3 now. Okay, because we're doing question 4 of 2021. That's Saturday, y'all. So now we're gonna move to the third one. Question 3. Okay, that's fine. Here's question 3. Question 3 is nice and easy. Okay, yeah, we're just dealing with this. This is normally really fast. Okay, question 3 is nice and easy, this one. All right, now, here's question 3. For every polynomial P of X, Q of X in P2 of X, put the inner product of P and Q to be defined by the integral of that. You may assume that this defines an inner product. Okay, assume that it defines an inner product. So you let R be equal to X squared. You let P be equal to this. Find the inner product in terms of A, B, and C. Okay, so we note that the inner product of P that QX becomes the integral of these PX, QX. PX, AX squared, BX plus C. Okay, that is, okay, that's not what I want to say. What I want to say is, we want to find this one. So we start with RP, and then what is R? R is what? Is actually exactly, okay, the integral of this. So you see, if this is P, P, Q, Q, R is going to be X squared. And then the second one, P. P is this one, which is AX squared plus BX plus C, dx. The integral from 0 to 1, which is AX1, AX to the 4th power, BX cubed plus CX squared dx. AX to the 5th power out of 5, BX to the 4th power out of 4, CX to the 3rd power out of 3. 0 to 1. Okay, we plug everything in here. So it's going to be A to the power 5. Okay, I have this school kid, Ronel, likes joining, and then he's sitting there with the friends, and they're busy talking when, okay, and still learning, still small, still in high school, still in grade 11. Okay, still in grade 11, that's the information I got. So out of 4. So this one is 3 out of 3 here. And everything here, you put zeros here. Right, so with that mentioned, we have the following. With that mentioned, we have the following. So that in the end, then we continue to then say hence, this inner product of RXPX, this inner product must be written in terms of what? Must be written in terms of ABC. Okay, must be written in terms of ABC, which is A out of 5, B out of 4, C out of 3. Okay, so we have exactly this part here. Right, so this one, you say, yeah, so that's A of 5, B out of 4, C out of 3. So this is the answer. So find this inner product in terms of A, B, and C, and therefore this is the inner product, and then we're done. Let's move to part B. Right, in part B, we need to find the length of R. We recall that the length of R is the same as the square root of Rx with itself. What is this? According to this definition of the inner product, is the inner product of Rx dx. It is the inner product of, what is Rx? Rx is x squared dx, and therefore this is the inner product, x to the 4th power dx, which is exactly 1 to 5 x to the 5th power from 0 to 1, which is 1 to 5, 1 minus 0, which is 1 to 5. Hence, this here, which is 1 to 5. So which means therefore the length of this, okay, its length Right. So obviously, I mean, this course is linear algebra, so it is 1 to 5 units. Right. So, and obviously at this point, because it is 1 to 5 units, once again, it is the square root of that, please. Right, because the square root of this and the inner product of this becomes the integral, but there's a big square root on everything. There is a square root on everything here. There is a square root on everything here. There is a square root on everything here. There's a square root on everything here. There's a square root on everything here. And then, okay, yeah. So you have the square root there, and then this one here. Sorry, we continue here, which is 1 to 5. And therefore, this is 1 divided by the square root of 5 units. Okay, so yeah. Okay, just take note of that. Obviously, this is a square root, and then the inner product is at the bottom of everything. So you have the big square root there that actually loiters around, and therefore this is the answer. It's actually 1 over square root of 5 units. Somebody can be like, hang on, okay, but yeah, I know this one are university guys. The university guys are not very strict when it comes to this, but now normally we do not leave answers with square roots in the denominator in mathematics. Okay, because a number that is square root in the denominator cannot be easily analyzed, so we need to rationalize. So we rationalize and make sure that the denominator is a rational number and the square root is in the numerator. It becomes a very nice number, but obviously these things are the same. So you have 5 units. So in principle, this is 1 over square root of 5 units. You can leave your answer like this. Yeah, but you don't have lots of time in the exam, and they can't even penalize you because you did not rationalize the denominator. You left your answer with a denominator that has not been rationalized. They really cannot be penalizing you for that part. So we move to the next point. Right. We move to part C. Okay, the top story is the same. Now, part C says the subset A of P2 is defined by these. A is ax squared plus bx plus c is an element of P2 of x, such that ax squared plus bx plus c is perpendicular to Rx. An incomplete description of A is given below. There should be an equation in the space in the place of the dots. Okay, there are dots here. Okay, these dots. All right. So there should be an equation in the place of the dots, so that you have A that has this polynomial ax squared plus bx plus c element of P2 of x, such that what? Write down this equation. All right. So this equation is going to arise from the fact that this is perpendicular to that. So if this is perpendicular to that, this equation would therefore mean that, right, an incomplete description of A is given below. There should be an equation in that. Yeah, all right. So obviously, now this is very important. And the equation would therefore that if this is perpendicular to that, and what would the equation be? The equation,
It would be that
yes, what do you think?
AX blah 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 times
Yes.
RX equals to 0.
Well done. That is exactly the answer. So well done there. So it would be that. So the equation would be that the inner product, because they're perpendicular. So the x squared plus bx, this inner product here is what? Is 0.
0. Oh yeah, the inner
Yes.
product. Sorry,
Yes. See, that's
I
fine.
always
So it would be the inner
forget.
product is 0. But now the examiner here expected much more than that, to say what is this gonna become. Okay, so we're gonna work it out. So now if you have, yeah, okay, because yes, because
Okay.
if these two vectors are perpendicular to each other, that means the inner product is 0. But we know that px qx is the integral from 0 to 1 qx dx, which means that you have ax squared plus bx plus c, and then it is with the r, rx. Okay, what is rx? You can already put this one. It's x squared. You can
It's
write
squared,
that.
yeah.
Right. So you have the integral from 0 to 1, and this is ax squared plus bx plus c, and then you have the rx, and the rx is x squared. X squared dx, like this. Right. So this is very important. But we're already saying this result is what? Is 0.
0.
We've already got something like this.
Yeah.
Did we not have the ax squared plus bx plus crx?
Yes.
Let's see, with something like that. No, it was rx and p, but p is this.
Yeah,
Okay.
P is the same.
But it's the same thing. So yeah, and
Yes.
what answer did we get here? We got this answer. We got this answer, and therefore the equation became, so it's going to be the same equation. So this
Yeah,
equation is a over 5, b over 4, c over 3. Okay,
yeah.
by some symmetry. So that's what we're going to put here. Right, so obviously there's no need for us, but now this is 0. And this equation we got here is actually such that we have a out of 5, b out of 4, c out of 3 equals 0. So, and this would mean a is ax squared plus bx plus c element of p2 of x. And then we have a out of 5, b out of 4, c out of 3 equals what? Equals 0.
0.
Okay. Yeah. So this is sort of, so the examiner expected this equation, okay, to be put, because it was already worked out in the previous question. So it was most certainly something that this examiner sort of anticipated to sort of include. Let's move to the next question. Okay, because this is the end of question 3.
Yeah.
Because it's the end of question 3, then we need to move to question 2.
Sure.
Right, we're just moving in reverse. Okay,
Yes.
and we're guided by the fact that maybe the last questions are a little bit more difficult, and therefore we need to spend a bit more time on those. Right, so, okay, let us look at this one here. Okay, let us look at this. Okay, you are given that we have linear transformations. The linear transformation T from P2 of X to M22R is what? It's a linear transformation, and that T1 is this, and those are the images. Now, find the image of this, right? Find the image of this particular matrix. Now, to find the image of this, there are a couple of things you need to obviously be able to take into account. What are the things? So it's very straightforward. You need to take actually the fact that we have t bx plus c. Okay, but we have a linear transformation. Linear transformation means that you can write a tx squared, b of tx, c of t1, like this. Right. So that in the end, then if you have t of ax squared plus bx plus c equals a, what is t of x squared? We already got it. Is this one here, which is exactly 2002 plus b of, what is tx? It's already 0, 1, minus 1, 0. What is t of 1? Is already minus 1, 0, 0, minus 1. Okay, with this mentioned, then we have what? We add everything. So it's going to be 2a minus c. 2a minus c. Then this one is minus b. And then we have this one, it's exactly b. And then this one is exactly 2a minus c, like this. Okay, so this is sort of the answer. I mean, obviously, then we're able to then say t of ax squared plus bx plus c. This t is actually 2a minus c minus b, b 2a minus c, and that becomes exactly the answer to this question. So we found exactly t of x squared plus bx plus c. We move to the next question. Right. So now the next question is this one here, which is part B. Give a basis for the range of t. Right, so to give a basis for the range of t, the couple of things we need to take into account. And obviously we need to, oh yeah, that's what exactly we've got. Because we remember that t of x squared plus bx plus c from the question we just solved now is actually 2a minus c minus b, and then we have 2a minus c like this. So a basis for the range is when we do what? It's when we split these things up. Right, so when we decide to split these things up, therefore that forms a basis for the range. But also there are a couple of ways to obviously determine the basis for the range. So, but now the basis for the range would be seen as follows. Right, so you can write it as ax squared plus bx plus c, and then you separate the things, like you have the a's alone, and then we have 2a here, 0, 0. And then obviously if you split this up, and now you're able to see these images, you'll get to the same thing in particular. So if you split this up, you'll get to these particular elements. One way, therefore, to see that is to then say a basis for the range is seen when you can, okay, you can pick like this. It's easy like that. Okay, there are duplicate vectors here. But you see, in general, then you need to first, do the linear thing. You must check linear independence. It's easier. Right. So, but you must discard it because this vector is the same as this vector. It's a multiple of this vector. So now it means, therefore, you can decide. You take this vector and also you take this vector and then you throw this one out. So that the basis would be, okay, a basis for the range of T is what? A basis for the range of T, you can take this one, you can take -1, 0, 0, -1, and then you also take 0, 1, -1, 0. Or you can take 1, 0, 0, 1, 0, 1, -1, 0. Or you can, yeah, okay, you throw this one away because it's the same. You just multiplied this by 2. Right, so obviously that would be a basis for the range. But I mean, you might not, some matrices are not easy to see, especially under exam conditions. You're under pressure. You need to check linear independence of the images of these. So lambda 1, lambda 2, lambda 3, you write everything and then see that you do not have, not all the scalars are 0. And then you cut this one out. Then you're left with 2. Then you check linear independence of this. You see that these two are linear independent. And then now you can take this or you can take that one, because if you write the scalars of the 3, then you realize that not all the scalars are 0 there. Okay, that's something that is very important. Let's look at the next question. Okay, that's fine. Yeah, just 1 second. Right, so if you look at what you need to do here in the next part, okay. Now, if you look at what you can do in the next part, right, give the kernel of T. Give the kernel of T and a basis for it. Right, remember that to write the kernel of T, the kernel of T contains things that are here. Contains, hey, there's this Ronel, this grade 11 kid is trying to join from time to time. Right, so we have ax squared plus bx plus c. So the kernel contains elements of the domain such that what? Such that the image of these things, bx plus c, the image of this is 0. Okay, the images are matrices. Right, so if you have exactly that, you can see that the grade 11 kid is just, yeah, okay, so now this is exactly what you have. So we have that the kernel of T is x squared plus bx plus c, so that the image of this is 0. So the kernel contains those elements that are mapped to 0 by T. Okay, so now what then exactly is the answer to that? So it means, therefore, you need to consider the image of this. What is the image of this? So for the kernel, okay, you write the kernel. Right, so for the kernel, you proceed as follows. Right, so you can write the kernel of T as ax squared bx plus c. What is the image of this? Okay, the image of this is going to be exactly 2a minus c minus bb, 2a. Please come again. All right, okay, yeah, just 1 second. And then now, okay, let's see what you can get. Right. Okay, I'm just going to another to another student.
Okay.
Yeah, first see what you can get. All right, because I'm finishing now. All right, so now, and then, yeah, all right. So now you have that the kernel of T contains all the things in the P2 of X, which is X squared plus BX plus C, so the image is 0. And then therefore it contains now the image of this of X squared plus BX plus C equals 0. Then you have the 0 vector here, but this 0 vector is the same as what? This. Right, so the 0 vector means therefore you have the following things. Right, so the 0 vector therefore is 0, 0, 0, 0. Okay, so with this then you are able to say that you have 2a minus c 0, you have b equals 0 for this one. You have minus b equals 0 for this one, and then you have 2a, okay, minus c equals 0. Okay, what we are seeing here is that these things are like repeating. Let me see here. Because this is 2a minus c. Okay, this is 2a minus c minus b minus b. But now what you're able to see here, from these two, you're able to see that b equals 0. And
Yes.
from these two, you're able to see that 2a is c, or you can see that c is 2a. Something like that, or you can write some half. But you're able to see that C is 2a from the first and the last. Okay? So if this is the case, what then are we able to achieve out of this? So thus we have ax squared plus bx plus c. Right, so which means that the b is 0. But simultaneously, we have that if the b is 0, and then c is what? C is 2a. Right, so yeah, that's fine. So you can then say the kernel is like this. So it means, therefore, we are dealing with the kernel of T. It means the kernel of T is going to contain B equals 0. Okay, if B is 0, then it means that we have ax squared, but B is 0, and then we have plus C, like this. Right, you have plus C. But C is equal to what? C is equal to 2a. So in the place of C, you can put twice A, such that the A is a real number. So this becomes the kernel of T, so that the kernel of T becomes what? Right, so it becomes exactly this. But if this is the case, then you can take out the A and then have x squared plus 2. Right, so you have x squared plus 2 such that the A is R, like this. And therefore, it means, therefore, the kernel of T is equal to the span, of x squared plus 2. You can write like this. So the kernel of T is equal to the span of the x squared plus 2, because you have the linear combination of just one vector. So now you can conclude and then say a basis for the kernel of T, is x squared plus 2. A basis for the kernel of T is what? Is x squared plus 2. Because we have defined the kernel, and the kernel of T is the span of this, or the kernel of T is equal to this, or the kernel of T is equal to this. But the basis for it is what?
It's just the...
Yes, a basis for it is x squared plus 2. Okay, it's x squared plus 2. Let's move to the next question, please. I'm sure this is clear, right?
Yes.
All right, good. Move to the next point. Right, so the next point is part D. Part D. Right, in part D, they need to find the matrix A representing T with respect to the ordered basis, this one, for P2 of X and M22R, respectively. Right, so to find a matrix A representing T with respect to the ordered basis. Right, so in other words, now there are two ordered bases. The basis for the P2, for the P2 of X is this one. This is the basis for the M22R. Okay, find the matrix. Okay, yeah, you use the same, the same key for the pattern. Okay, right, so find the matrix A representing T with respect to the ordered bases. Right, so now let us find this matrix. Is a very, very interesting one. This one that we always are able to always find. So at this point, now, if you are mapping P2 of X to M22R, right? So in other words, we've seen that if you now, how would you then be in a position to write that out until we write these as follows? Now, there are a couple of things, obviously, that you need to take into account. It's the fact that the images of T1, Tx, and Tx squared have already been given. Simultaneously, you are able to then say any polynomial that is of the form ax squared can be written like that. We've already seen the actual formula there. And now, as a consequence, we then are able to make the following observation, that we can be in a position to write the following. Right, I want us to be able to write the following expression for ourselves. Right, so I want us to take note of something here as we write the fact that these are ordered bases, and these bases are ordered, you can write them, they're ordered from left to right. Right, since they're ordered from left to right, it means therefore if you are able to take T that acts on P2. Okay, let's write T of 1. What is T of 1? T of 1 is this. Okay, if T of 1 is this, and you can write T2, we're gonna actually write T of X is that, and T of the next one is that. But if this is the case, it means that these can be written as a linear combination of this. Right, that's what we say. Could write, we put some scalars there where these are real. Right, and then we have C like that, and then we have D like that. Okay, we start with this one. Okay, we need to write all the equations like Tx. Okay, we might actually be fast to see the pattern here. Okay, because Tx is what? Tx is 0, 1, minus 1, 0. And then you can, yeah, different scalars per second. 1, 0, 0, 0. PQ, RST, 0, 1, 0, 0. R 0, 0, 1, 0. S 0, 0, 0, 1. Tx squared, which means that 2002. Okay, so now we can write X. Okay, which is the last one? This one. You can write X of the first one, 1, 0, 0, 0. Y 0, 1, 0, 0. Z 0, 0, 1, 0. W 0, 0, 0, 1. Okay, so if this is the case, can you see any patterns so that we can quickly? Okay, we must solve these systems here. And then if we solve these systems, we must be able to get the answers to this. But now it's a little bit easy, tricky. Okay, let's see. Okay, let's look at the first one. Like the first one is going to be A. Okay, it's going to be A because the rest are 0. Right. So you're going to have that A is equal to what? A is equal to minus 1. Then for this, and that. Then for the second one, this one is going to be B is equal to 0. And then this one, 0, 0, C is equal to 0. And then if you deal with the D part, okay, this one is D and the rest is 0. D is equal to -1. Okay, now this is what you get. Oh, now if you check this carefully, the question is, out of this, what can you get? So now it means that this is going to produce, it's going to produce a matrix. Okay, well, let's write the matrix here because yeah, we have a little bit of space here. So now we're going to call this matrix a special name. We're going to call it the matrix A. Right, so now we're going to call it the matrix A. So this one is going to produce, because it's the first one, it's going to produce the first column of this. So the column is going to be A, B, C, D. A, B, C, D, which is -1, B 0, C 0, D is -1. Okay, that is what we get. Next, let's come to this one. What is this one here? This one is going to be P, but the rest is 0. You can see that P is what? P is 0. And then here you're able to see that Q is 1. And then this one, you're able to see that R is -1. And then S is 0. Okay. So now we take these things, you put them in order here. Okay, because we compare with this side, right? We get everything from here. So now the P, Q, R, S, they're going to form a column here. P is 0, Q is 1, R is -1, S is 0. Just like that. And then, okay, it's exactly the same as what your teacher got, what your lecturer got. Right. So the next thing now, you're getting the bottom one. So here it's going to multiply out. So we're going to we have X for this one, 0, 0, 0. And you're able to see that X is what? X is 2.
X is 2.
And then now you're going to come here and we have, yeah, Y is 0. And then now what else? Okay, come to this one is Z. So Z is 0. Okay, Z is 0. And then what else? W 2. X is what? 2. Y is 0. Z is 0. W is what? W is 2. Check that one. Yeah, it's exactly the answer your lecturer got. So in this way, we are finding exactly the matrix representation. So now find the matrix A representing T with respect to the ordered basis, and this is the matrix A, right? And this is the end of question 2, because if I continue right now like this, okay, yeah, then we meet question 3, okay, because I've loaded all the questions here. Okay, so now because of this and because of our time, this is the end of question 2. Yeah, we had a chance to do question 2, we had a chance to do question 3, we had a chance to do question 4. And now we could just move to question 1, but I can see that obviously we are beyond time. It's like 17:23. Okay, because
yeah, I can do question 1 on my own, and then I'll ask if there's something that
that's fine. Yes, that's okay. That's okay. Yeah, we have taken like some 2 hours now already. Okay.
Okay, yeah.
Right. Thank you so much, but we must thank you for joining us. It was awesome having this discussion right now. And then we actually, obviously, we'll keep in touch for tomorrow. Please take your schedule tomorrow. Either we have our lesson, either we have our lesson at the usual time, 7 p.m., or we can have double.
Yeah, we can have double.
Yeah,
we can have double so that you can maybe at 10 if that's fine.
Yeah, definitely. At 10, maybe we can do something, because I want us to cover math, but I want to have the study guide review. You know,
tomorrow at 10, we can have the study guide review. Yeah,
and we like go through the study guide, the theorems we discuss.
Yeah.
You know, the study guide in general in terms of what it covers. But also we look at the study guide in comparison to what? In comparison to the exams we've seen. So we have a chance to see what is like important in the study guide, what kinds of things you need to focus on, what theorems sort of like
I need to remember
a lot, things like that. Okay, right. But thank you. Yeah, thanks a lot for joining us. It was awesome having this discussion. Until tomorrow at 10 a.m. Take care and goodbye. We're gonna send the recording today.
Okay, thank you so much. Bye.
Okay, thanks, dear. Goodbye. Goodbye. All the best. Thank you.
Bye.